Okay, so here's where we got in the last video. We had this system, we confirmed it was Hamiltonian. We found a Hamiltonian function for it, so we know that the solutions are our level curves, but we said we weren't entirely sure what that was going to look like, and so we decided we were going to classify our two equilibrium points. So, if we do that, when I linearize things, I'm going to get u prime v prime. Remember, what that does is that just translates the equilibrium point to put it at the origin in the uv plane. So this one is in the origin in the xy plane, so we're not really moving it. This one we would move one to the left to put at the origin in the uv plane. This is going to equal my Jacobian matrix, which I'll call J, times uv. Okay. And the Jacobian matrix is the partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. Okay. So just looking at that Jacobian matrix, because that's really all we need to look at in order to classify our systems. If I take a look at the partial of f with respect to x, that's 0. Partial with respect to y is going to be 1. Partial of g with respect to x is going to be 1 minus 2x. And partial of g with respect to y is going to be 0. And anytime we have a Hamiltonian system, these two are going to be opposites, because these are the, well, one of them is the mixed second partial of h, and the other one is the opposite of the mixed second partial of h. Okay, excellent. So if I take a look at this, the Jacobian matrix at 0, 0 would be 0, 1, 1, 0. Okay, so I need some more space, so I'm going to remember that that's my matrix and just erase, let's see, I don't want to keep that up. So J is 0, 1, 1 minus 2x, 0. Okay. All right, so if I'm working with this matrix, 0, 1, 1, 0, my characteristic equation is going to be lambda squared. The trace is 0, so minus the trace times lambda. That piece drops out, and that always happens with a Hamiltonian system. The lambda term in the characteristic equation is gone. Okay, that's because these guys are opposites, so the trace will always be 0. Determinant is nothing minus 1, so we get lambda squared minus 1 is equal to 0. So lambda squared is equal to 1, so lambda is going to be plus or minus 1. Now, what that tells me is that this is going to be a saddle. Okay, so 0, 0 is a saddle. And that is a case where the linearization works. Okay. Remember, the two cases where linearization can fail are for a general system. If we get a center, we don't know if we have a center, a spiral source, or a spiral sink. But for a Hamiltonian system, if the linearization gives us a center, then we have that in the nonlinear system as well. So the only time that it fails in a Hamiltonian system would be if I get 0 as an eigenvalue. Okay, so let's find the Jacobian at 1, 0, which is my other equilibrium point. So that's going to be 0, 1. 1 minus 2 times 1 is going to be negative 1, 0. Okay, so my characteristic equation is lambda squared. Once again, the trace is 0. The lambda term drops out. The determinant is 0 minus negative 1, so plus 1 equals 0. So lambda squared is 1, so lambda is going to be plus or minus I. Now, when I get a purely imaginary numbers as purely imaginary numbers. When I get purely imaginary numbers as my eigenvalues, I know that that means that I've got a center. If this wasn't a Hamiltonian system, I would have narrowed it down to this is either a center or a spiral source or a spiral sink. Since it's Hamiltonian and Hamiltonian systems, the solution curves have to be the level curves for this function, and those aren't going to spiral towards or away from something. So I know that 1, 0 is a center. So we're able to classify them. So I'm expecting solutions to sort of spiral around this, and I'm expecting solutions here to behave so that they're sort of coming closer and then further away and closer and further away, etc., etc. So if I actually grab my textbook, I'll refer you to the correct page here. The phase portrait for this is actually on page 493. Okay. And it's kind of neat. We see a solution curve like so, oriented, it turns out, going clockwise. We see something very interesting here. This is an equilibrium solution, remember. So we see a solution curve that leaves that equilibrium solution, loops around the other one, and comes back to that equilibrium solution. That's got a name. We'll take a look at that in a moment. We've got a solution curve coming in like so. We've got a solution curve leaving like so. And then over here, our solution curves kind of curve like so. And out here, they come around like so. I definitely didn't know that that was what the level curves of this particular function looked like, but it's kind of neat, okay? When you have a situation like this, remember we call these solution curves that approach or leave this equilibrium solution that's a saddle, we call those separatrices. And when I have a separatrix leave and then come back to the same equilibrium solution, we call that a saddle connection. A kind of neat thing that can happen, so I wanted to make sure that I pointed that out. Okay. So I can really see, yep, that's a center. I do have some solutions that are just curving around it, and this really does behave like a saddle. With the separatrices, I've got two curves coming in, two curves leaving. It just so happens that one of the ones that's leaving is the same as one that's coming in, and then all the other curves sort of come closer and go away, come in and go away, things like that. Okay, excellent, fun system.